The National Electrical Code, or NEC, Article 314 covers electrical metallic tubing, or IMT. Section 314.24 details supports in other than seismic areas, while Section 314.28 specifically addresses supports in seismic areas. Article 362 pertains to rigid metal conduit, or RMC. Section 362.24 outlines supports in other than seismic areas, and Section 362.28 focuses on supports in seismic areas. Article 370 concerns outlet device, pull, and junction boxes. Section 370.13 discusses boxes and conduit bodies, and Section 370.70 covers boxes, conduit bodies, and fittings and floors. Article 500 addresses flexible cords and cables, with Section 500.8 covering underground installations. IEE 142-2007 is the IEE recommended practice for grounding of industrial and commercial power systems. NFPA 70E is the standard for electrical safety in the workplace. The International Building Code, or IG, and the California Building Code, or CBC, are also relevant. A paper titled Seismic Performance of Pipelines and Conduits, a review by S.P. Singh, published in the Indian Geotechnical Journal, Volume 43, Number 3, July 2013, provides additional insights. The primary concern is whether compression fittings are acceptable in the seismic 3 zone when the engineer specified GRC with threaded fittings. The NEC provides guidelines for conduit installation, including specific requirements for seismic areas. It is crucial to consult the sections dedicated to seismic considerations within each relevant article, such as Article 314 for AMT and Article 362 for RMC. These sections will outline the acceptable methods for supporting and securing conduit in seismic zones. The listing of compression fittings is important. If the compression fittings used by the contractor are listed for use in seismic applications, this would generally indicate that they meet the necessary standards for seismic integrity. Look for markings or certifications on the fittings that indicate compliance with relevant seismic standards. The IBC and CBC also contain provisions related to seismic design and construction, including requirements for electrical systems. These codes may reference specific standards or testing protocols that conduit systems and fittings must meet in seismic zones. Consulting these codes can provide additional clarity on the acceptability of compression fittings. The IEE 142-2007, while primarily focused on grounding, can also provide relevant information on ensuring the overall integrity and reliability of electrical systems in industrial and commercial settings, which is particularly important in seismic zones. The seismic integrity of a raceway system depends on several factors. Firstly, the type of conduit used, which in this case is GRC. Secondly, the fittings used to connect the conduit sections. Thirdly, the support system for the conduit run. And fourthly, the overall design and installation practices. Threaded fittings generally provide a more robust connection compared to compression fittings, as they create a direct mechanical connection between the conduit sections. However, compression fittings can be acceptable if they are specifically listed and labeled for seismic applications. The listing ensures that the fittings have been tested and certified to withstand the forces associated with seismic events. To determine the acceptability of the installed compression fittings, firstly, verify the listing status of the fittings. Check the manufacturer's documentation or the fitting itself for markings that indicate compliance with seismic standards. Secondly, review the project specifications and drawings. Determine if the engineer's specification of threaded fittings was a mandatory requirement or a recommendation. If the specifications explicitly prohibit the use of compression fittings, then the contractor may be in violation of the contract. Thirdly, consult with a qualified engineer. Engage a structural or electrical engineer with experience in seismic design to evaluate the installed raceway system. The engineer can assess the suitability of the compression fittings based on the specific seismic loads and soil conditions at the site. Fourthly, consider the support system. Ensure that the conduit run is adequately supported and braced to resist seismic forces. The NEC and the IBC provide guidelines for conduit support spacing and methods, which should be strictly followed. Fifthly, review the installation practices. Verify that the compression fittings were installed correctly according to the manufacturer's instructions. Proper installation is critical to ensure the fitting's ability to withstand seismic forces. If the compression fittings are not listed for seismic applications, or if there are concerns about the installation quality, it may be necessary to replace them with threaded fittings as specified by the engineer. Alternatively, additional bracing or support may be added to the conduit run to enhance its seismic resistance. The Singh paper on seismic performance of pipelines and conduits provides a comprehensive overview of the factors that influence the seismic behavior of these systems. It discusses the different types of conduit and fitting connections, as well as the effects of seismic ground motion on buried and above-ground pipelines and conduits. This paper can serve as a valuable resource for understanding the technical aspects of seismic design for raceway systems. Consulting with a qualified engineer is crucial to determine the specific requirements for a particular installation in a seismic 3 zone. The engineer can take into account the site-specific conditions, the type of equipment being served by the raceway system, and the applicable codes and standards to develop a safe and reliable design. A qualified engineer can perform calculations to determine the expected seismic forces on the conduit system. They can then select appropriate fittings and support systems that can withstand these forces. The engineer can also provide guidance on proper installation practices to ensure that the raceway system performs as intended during a seismic event. In addition to the NEC and the IBC, state and local building codes may also have specific requirements for electrical systems in seismic zones. It is important to consult these codes to ensure compliance. Some jurisdictions may require special inspections or certifications for electrical installations in seismic zones. The inspector can verify that the installation meets the applicable code requirements and that the fittings and support systems are properly installed. The owner's concerns about the seismic integrity of the raceway system are valid, especially given the engineer's specification of threaded fittings. It is important to address these concerns by conducting a thorough evaluation of the installed system and taking corrective actions if necessary. The goal is to ensure that the raceway system can withstand the forces associated with a seismic event and protect the electrical equipment it serves. The NEC provides minimum requirements for electrical installations, but it is ultimately the responsibility of the design engineer and the contractor to ensure that the system is safe and reliable. In seismic zones, this responsibility is even greater, as the consequences of a failure can be severe. Compression fittings, while potentially acceptable if listed for seismic use, require careful consideration and verification. The engineer's initial specification for threaded fittings suggests a preference for a more robust connection method, likely due to concerns about seismic performance. Therefore, a thorough review and possibly a professional engineering assessment are warranted to ensure the system's integrity. Firstly, determine if the local building codes have any specific amendments or additions to the NEC or IBC regarding seismic requirements for electrical systems. Local codes can be more stringent than the national codes and may provide further guidance on acceptable fitting types. Secondly, request the contractor to provide documentation demonstrating that the installed compression fittings are listed and labeled for seismic applications. This documentation should include the manufacturer's specifications, testing reports, and any certifications from recognized testing laboratories. Thirdly, if the documentation is not available or if there are any doubts about the suitability of the compression fittings, consider performing pull-out tests on a sample of the installed fittings. These tests can verify the mechanical strength of the connections and ensure that they can withstand the expected seismic forces. Fourthly, evaluate the overall configuration of the conduit system. Are there any long, unsupported spans that could be susceptible to excessive movement during a seismic event? Are there any sharp bends or offsets that could concentrate stress on the fittings? Fifthly, consider the consequences of a failure of the raceway system. Would a failure result in a loss of power to critical equipment or systems? Would it create a safety hazard for building occupants? The answers to these questions can help determine the level of risk associated with the use of compression fittings and the need for corrective action. Sixthly, engage a qualified third-party testing laboratory to perform a seismic analysis of the raceway system. This analysis can provide a more detailed assessment of the system's performance under seismic loading conditions and identify any potential weaknesses. Seventhly, if it is determined that the compression fittings are not suitable for the application, develop a plan to replace them with threaded fittings or to provide additional support and bracing for the conduit system. This plan should be developed in consultation with a qualified engineer and should comply with all applicable codes and standards. The key takeaway is that while compression fittings can be acceptable in seismic zones if they are properly listed, labeled, and installed, it is crucial to verify their suitability for the specific application and to address any concerns about their seismic performance. Consulting with a qualified engineer and conducting a thorough evaluation of the installed system are essential to ensure the safety and reliability of the electrical system in a seismic zone. The integrity of the electrical system is paramount, especially in regions prone to seismic activity. The initial specification of GRC with threaded fittings likely stemmed from a conservative design approach aimed at maximizing the system's resilience to seismic forces. Deviation from this specification warrants a rigorous evaluation to ensure that the substituted compression fittings provide an equivalent level of performance and safety. Firstly, obtain a comprehensive submittal package from the contractor detailing the specifications of the compression fittings used. This package should include the manufacturer's name, model number, material composition, and relevant testing data. Secondly, scrutinize the testing data to verify that the fittings have been subjected to seismic qualification testing in accordance with industry-recognized standards such as IEE 693 or ICC ES 156. These standards define the procedures for simulating seismic events and evaluating the performance of electrical equipment. Thirdly, pay close attention to the performance criteria used in the seismic qualification testing. Fittings should be able to maintain their structural integrity and electrical conductivity under the expected seismic loads. Look for evidence of any failures or degradation during the testing. Fourthly, compare the performance characteristics of the compression fittings with those of threaded fittings. Threaded fittings generally provide a higher level of resistance to pull-out forces and bending moments, which are critical considerations in seismic zones. Fifthly, assess the installation practices employed by the contractor. Were the compression fittings installed in accordance with the manufacturer's instructions? Were the fittings properly tightened and secured? Any deviations from the recommended installation procedures could compromise the seismic performance of the system. Sixthly, consider the potential for corrosion. GRC is typically galvanized to protect against corrosion, but the compression fittings may not have the same level of corrosion resistance. In a corrosive environment, the fittings could degrade over time, reducing their ability to withstand seismic forces. Seventhly, evaluate the grounding and bonding of the raceway system. Proper grounding and bonding are essential for ensuring electrical safety and minimizing the risk of equipment damage during a seismic event. Eighthly, conduct a thorough visual inspection of the installed raceway system. Look for any signs of damage, such as cracks, dents, or loose connections. Ninthly, if there are any concerns about the suitability of the compression fittings, consider performing non-destructive testing, such as ultrasonic testing or radiography, to assess the internal integrity of the fittings. Tenthly, document all findings and recommendations in a comprehensive report. This report should be shared with the owner, the engineer, and the contractor to ensure that all parties are aware of the potential risks and the proposed corrective actions. The decision to accept or reject the use of compression fittings in a seismic zone should be based on a thorough evaluation of all relevant factors, including the listing status of the fittings, the project specifications, the applicable codes and standards, and the professional judgment of a qualified engineer. The safety and reliability of the electrical system should be the paramount consideration.